So a tensile test is performed on a cylindrical sample with an original diameter of 20 millimeters. The measured stress strain curve is shown below. What is the shear modulus of the material if the sample was measured to have a reduction in diameter of 0.009 millimeters at the instant when 100 kilonewtons was applied? So our eventual goal is to work out what G is, and I've written out a bunch of different equations that we have to use within the stress and strain space. So we can see that G appears in this top equation and this bottom equation. The one that we're going to need to eventually apply is going to be the top one. Okay, if we want to use the bottom one, we need to have some shear properties of our material. But what we've been told is we're doing a tension test, okay, where we have some sample and it gets stretched. So that means that we're not actually causing any shear in the material. That would only occur if we were pulling it side to side. So this one is not going to be useful to us for this question, and we're going to need to fill in this top equation. So in order to do that, we need to know Young's modulus, and I think that's a good starting point for us. So we've been given the normal stress versus normal strain curve, and we know that Young's modulus is the gradient through this linear section. So we can determine what it is. It's equal to the change in stress divided by the change in strain. We're going to use these 2 points. Obviously this is 0, 0. And we end up with an answer for Young's modulus of 203,000, and the units are going to be in megapascals. So we've now got E in the equation. The other one that we need to find is our Puissance ratio. And this one is a little bit more involved because we have to go through a few more steps in order to find it. So Poisson's ratio is also in this equation here, which relates together the lateral and the longitudinal strain. So we're going to need to find both of these in order to calculate Poisson's ratio. So let's start with trying to get the longitudinal strain. We are told that we have a change in the diameter of 0.009 millimeters at the instant when 100 kilonewtons is applied. So we're going to need to figure out what's going on when we have this 100 kilonewtons of force. So I'm going to start with finding the stress that's caused when we have 100 kilonewtons. So stress is equal to the force divided by the area. So I'm going to put this into newtons, and our cross-sectional area is based on a diameter of 20 millimeters. So we find out that we're causing a stress in our material of 318.3 MPa. So if we come over to our stress strain curve and try and make sense of that, we're going to be sitting about here, 318. And what we need to do is figure out the strain that this corresponds to down here. So this point, I'm going to call it E long. Okay, remember that when you have a stress strain curve, this E is always the long one that we're plotting. So we should be able to determine what this is based on the fact that we know the gradient of the graph is this 203,000 MPa. So if I reapply Young's modulus equation, we know that it's 203,000. The change in stress, so we're going to be looking between this point, and I'm going to pick the point 0, 0, but equally you could look at 406 as well. So it's going to be 318.3, take 0, divided by that longitudinal strain we're looking for, take 0. And we found out that this is about 0.001568 for E long. So now what we need to do is work out our lateral strain, because then we're going to be able to calculate Poisson's ratio. So the lateral strain is also included in this equation here, where it's equal to the change in the diameter divided by the initial diameter, and we know that we have 0.009 change. So subbing in, now I'm going to put this in as negative because we know it's getting smaller in that direction. And our original diameter was the 20 millimeters. So we can calculate that we have a lateral strain of negative 0.00045, Remembering this negative is here because it's getting smaller in that direction. So now that we know E long and E lat, we can work out Poisson's ratio. So substituting in, it's going to be the negative of negative, so double negative there. So we end up with a positive answer, and it's about 0.287. So the final step is to convert this into our shear modulus, and we have this equation as discussed. So we've now got everything we need. We can just substrate into it. So we said that Young's modulus before was 203,000. And Poisson's ratio we said was 0.287. So we end up with a final answer for G of 78,866, And because Young's modulus up here was in megapascals, this answer is also going to come out in megapascals. If you want to round it because it is relatively big, you can. It's the same as 78.9 gigapascals. So that would be our final answer. So that's all there is for that question, and see you in another video.